It's a pleasure to speak to you today. My name is Dorit Donoviel, and I have the pleasure of being the Executive Director of the Translational Research Institute for Space Health, or TRISH for short. We are a consortium of Baylor College of Medicine, Caltech, and MIT, and we are a NASA-funded organization that makes grants to universities and companies throughout the United States that can keep humans healthy in space, doing research in health and human performance. So we're talking to you today because space is such an amazing opportunity for us to do innovations in health and biology. It's a very provocative environment because the human body has to adjust to this novel environment with many different changes in the environment. So we are going back to the moon. We haven't been for 50 years. And for the last 20 years, humans have been living in space and learning how to stay healthy. And we've learned a lot. We've learned that humans can adapt to the zero-G environment quite well. They undergo changes to every single physiological system. And they have to exercise to keep their muscles and their bones and their hearts healthy. And there are some changes that occur that we are learning that resemble the early stages of some conditions on Earth that are related to deconditioning of bones and muscles and hearts. We're also seeing some fluid shifts that occur towards the head because of the lack of gravity, and we're seeing some very interesting ocular and brain changes as well. In addition to the body adapting to the spaceflight environment and its lack of gravity, we also have to contend with space radiation. And while we are still within the protection of our atmosphere and our magnetosphere, the humans that live on the International Space Station are still well protected from all the space radiation. But once we leave low Earth orbit and go back to the moon and perhaps even to far off destinations like Mars, our astronauts and our space explorers will be exposed to galactic cosmic rays, which are really damaging to both biological tissues, but also electronics as well. We really cannot fully shield for all of these particles. And in fact, inadequate shielding can cause a bigger problem by fractionating some of these particles and creating multiple hits instead of just a single hit by a particular ion. Now, we know that radiation can cause damage to many tissues in the body. Some of them are so sensitive, like the brain, that even very low doses of simulated space radiation in simulation studies with animals have caused significant damage, memory loss, and learning difficulties, etc. NASA's concerned about not just acute radiation syndrome from a high dose of radiation, but also the degenerative effects to the brain, to the heart, to the bones, to the muscles, and long-term effects of increasing the risk for cancer to occur. Now, when we go back to the moon and we are exposing our humans to the changes in the gravitational forces that reduce gravity on the moon surface, or the space radiation environment, we're not going to be able to take everything that we take for granted, even on the ISS with us. As you can see here, an astronaut is very limited in the amount of equipment and even materials that he has or she has to stay healthy. Whatever we take with us is very confined and limited, and particularly when we go to a place as a far off destination such as Mars, we're not going to be able to resupply that crew with food, with medications, with clean underwear. Whatever they take with them is what they have to contend with over that 1.5 to 3 year mission. No resupply. Whereas right now we've become quite dependent on Earth, on the International Space Station. The crews received resupply every 1 to 2 months. They get fresh foods, they get new materials, they get new equipment that they could replace if something breaks, etc. So now you can see that as we're solving for a future where humans can explore deep space and go on long duration missions, we're going to require something different than what we have today. Now, for example, medications. What we bring with us on this long journey to Mars or even the moon is what we have. And if those medications have a short shelf life, which many of them do, or they get degraded by the space radiation environment, or we simply didn't bring the right medication for, or maybe even the right antibiotic for a particular bacteria strain that all of a sudden grew up in this closed-looped environment, we need to figure out a way to provide medications on the spot. The foods that we're going to be dependent on, we all know that eating a healthy diet filled with nutrients from plants in particular is really critical to maintain health. And we take that for granted here on Earth. There's a lot of microbiome components that we know also are critical to maintaining health. When we go on long duration space missions, our food system really is just pre-packed foods, and the pre-packed foods, in order to keep them sterile, have to be treated in such a way that it may kill many of the healthy microbes that we need for a balanced diet. And so you've seen some images of astronauts growing lettuce in space and peppers. The problem is that we haven't figured out a way to scale that up so that we really can provide fresh foods to the astronauts. And we're not going to have those resupply missions, like I mentioned earlier, on a deep space mission to Mars or even the moon. So how do we deliver to a crew over a 1.5 to 3 year mission fresh nutrients, things that are not labile, that we take for granted? How do we feed people, whether it be on the way to Mars, but maybe even in places on Earth where there is no ability to have agriculture? Like, for example, if it's in the middle of a desert and you have communities living somewhere where they really can't grow foods like this very easily. And finally, those crews are going to need a source of protein that is also stable, shelf stable, and healthy for them. And so many of the pre-packed meat-containing pouches for the food for space actually have the shortest shelf life. And so being able to provide those crews with an ability to create protein as needed in a sustainable way, again, is forcing us to think about a new way to feed people. So we're really excited about synthetic biology and being part of the SynBioBeta conference because the organizers saw the connection between space being such an important forcing function for innovation and us approaching the synthetic biology community to help us solve some of these difficult challenges. And in doing so, we not only solve those problems for the deep space exploration crews, but we may even start to look at ways to increase our resilience to environmental insults like aging or even certain environmental toxins that we experience here on Earth. And so longevity could actually be an offshoot or an application, what we call the Earth application, from some of the space health research that we will be supporting. In addition, being able to use the microbiome not just to regenerate itself in a healthy way and in a personalized manner to keep individuals healthy according to their specific needs in those conditions in space, under the conditions of having space radiation be a concern for them, and in zero G, we can also use the microbes to generate some of the things like, for example, the medications, the nutrients, the foods, some of the neurotransmitters which we may need in order to keep our crews emotionally healthy while they're isolated for such long periods. So the microbiome holds a lot of promise as well for us. The synthetic biology community is also working on doing 3D bioprinting. So creating not just steaks in space or meat products that can be good sources of protein for our crews and give them a feeling of eating real meat as opposed to just prepackaged everything. But also being able to 3D bioprint certain medications or nutrients or other objects or things that could be used in 3D printing other things, maybe even parts for their exercise machine or for the toilet, in addition to bioprinting biological materials that could be important as well, maybe replacing a particular organ on a space mission if that is needed as well. So with that, I'd like to close by saying that we are really excited to be partnered with the SynBioBeta family and all the researchers in really kind of pushing the limits on our ability to sustain ourselves, to live healthy, providing our own food, nutrients, medications, and our ability to remain resilient in any environment where we live, whether it be off the planet or on the planet. And if you want to engage with us and see what funding opportunities we have, please look at our website. Feel free to contact me as well. Thank you.